Part 4: Dangerous Planet. The history of any one part of the Earth, like the life of a soldier, consists of long periods of boredom and short periods of terror. British geologist Derek V. Ager. Chapter 13: Bang. People knew, for a long time, that there was something odd about the earth beneath Manson, Iowa. In 1912, a man drilling a well for the town water supply reported bringing up a lot of strangely deformed rock, crystalline class breccia with a melt matrix, an overturned ejecta flap, as it was later described in an official report. The water was hot, too. It was almost as soft as rainwater. Naturally occurring soft water had never been found in Iowa before. Though Manson's strange rocks and silken waters were matters of curiosity, 41 years would pass before a team from the University of Iowa got around to making a trip to the community, then as now a town of about 2,000 people in the northwest part of the state. In 1953, after sinking a series of experimental bores, university geologists agreed that the site was indeed anomalous and attributed the deformed rocks to some ancient, unspecified volcanic action. This was in keeping with the wisdom of the day, but it was also about as strong as a geological conclusion can get. The trauma to Manson's geology had come not from within the earth, but from at least 100 million miles beyond. Sometime in the very ancient past, when Manson stood on the edge of a shallow sea, a rock about a mile and a half across, weighing 10 billion tons and traveling at perhaps 200 times the speed of sound, ripped through the atmosphere and punched into the earth with a violence and suddenness that we can scarcely imagine. Where Manson now stands became in an instant a hole 3 miles deep and more than 20 miles across. The limestone that elsewhere gives Iowa its heart, mineralized water, was obliterated and replaced by the shocked basement rocks that so puzzled the water driller in 1912. The Manson impact was the biggest thing that has ever occurred on the mainland United States, of any type, ever. The crater it left behind was so colossal that if you stood on one edge, you would only just be able to see the other side on a good day. It would make the Grand Canyon look quaint and trifling. Unfortunately for lovers of spectacles, 2.5 million years of passing ice sheets filled the Manson crater right to the top with rich glacial till, then graded it smooth, so that today the landscape at Manson, and for miles around, is as flat as a tabletop, which is of course why no one has ever heard of the Manson crater. At the library in Manson, they are delighted to show you a collection of newspaper articles and a box of core samples from a 1991 two drilling program. Indeed, they positively bustle to produce them, but you have to ask to see them. Nothing permanent is on display, and nowhere in the town is there any historical marker. To most people in Manson, the biggest thing ever to happen was a tornado that rolled up Main Street in 1979, tearing apart the business district. One of the advantages of all that surrounding flatness is that you can see danger from a long way off. Virtually, the whole town turned out at one end of Main Street and watched for half an hour as the tornado came towards them, hoping it would veer off, then prudently scampered when it did not. Four of them, alas, didn't move quite fast enough and were killed. Every June now Manson has a week-long event called Crater Days, which was dreamed up as a way of helping people forget that unhappy anniversary. It doesn't really have anything to do with the crater. Nobody's figured out a way to capitalize on an impact site that isn't feasible. Very occasionally, we get people coming in and asking where they should go to see the crater, and we have to tell them that there is nothing to see, says Anas Shlapkol, the town's friendly librarian. Then they go away kind of disappointed. However, most people, including most Iowans, have never heard of the Manson craters. Even for geologists, it barely rates a footnote. But for one brief period in the 1980s, Manson was the most geologically exciting place on Earth. The story begins in the early 1950s when a bright young geologist named Eugene Shoemaker paid a visit to Meteor Crater in Arizona. Today, Meteor Crater is the most famous impact site on Earth and a popular tourist attraction. In those days, however, it didn't receive many visitors and was still often referred to as Barringer Crater, after a wealthy mining engineer named Daniel M. Barringer, who had staked a claim on it in 1903. Barringer believed that the crater had been formed by a 10 million ton meteor, heavily freighted with iron and nickel, and it was his confident expectation that that the meteor that he would make a fortune digging it out, unaware that the meteor and everything in it would have been vaporized on impact. He wasted a fortune, and the next 26 years cutting channels that yielded nothing. By the standards of today, crater research in the early 1900s was a trifle unsophisticated, to say the least. The leading early investigator, G.K. Gilbert of Columbia University, modeled the effects of impacts by flinging marbles into pans of oatmeal. For reasons I cannot supply, Gilbert conducted these experiments not in a laboratory at Columbia, but in a hotel room. Somehow, from this, Gilbert concluded that the moon's craters were indeed formed by impacts, in itself quite a radical notion for the time, but that the Earth's were not. Most scientists refused to go even that far. To them, the moon's craters were evidence of ancient volcanoes and nothing more. The few craters that remained evident on the Earth, most had been eroded away, were generally attributed to other causes or treated as flaccularities. By the time Shoemaker came along, a common view was that meteor crater had been formed by an underground steam explosion. Shoemaker knew nothing about underground steam explosions. He couldn't. They don't exist. But he did know all about blast zones. One of his first jobs out of college had been to study explosion rings at the Yucca Flats nuclear test site in Nevada. He concluded, as Beringer had before him, that there was nothing at Meteor Crater to suggest volcanic activity, but that there were huge distributions of other stuff, anomalous fine silicas and magnetites principally, that suggested an impact from space. Intrigued, he began to study the subject in his spare time, working first with his colleague Eleanor Helen and later with his wife Caroline and associate David Levy. Shoemaker began a systematic survey of the inner solar system. They spent 1 week each month at the Palomar Observatory in California looking for objects, asteroids primarily, whose trajectories carried them across the Earth's orbit. At the time we started, only slightly more than a dozen of these things had ever been discovered in the entire course of astronomical observation. Shoemaker recalled some years later in a television interview. Astronomers in the 20th century essentially abandoned the solar system, he added. Their attention was turned to the stars and the galaxies. What Shoemaker and his colleague found was that there was more risk out there, a great deal more, than anyone had ever imagined. Asteroids, as most people know, are rocky objects orbiting in loose formation in a belt between Mars and Jupiter. In illustrations, they are always shown unexisting in a jumble, but in fact, the solar system is quite a roomy place and the average asteroid actually will be about 1.5 million kilometers from its nearest neighbor. Nobody knows even approximately how many asteroids there are tumbling through space, but the number is thought to be probably not less than a billion. They are presumed to be a planet that never quite made it, owing to the unsettling gravitational pull of Jupiter, which kept and keeps them from coalescing. When asteroids were first detected in the 1800s, the very first was discovered on the first day of the century by a Sicilian named Giuseppe Piazzi. They were thought to be planets, and the first two were named Ceres and Pallas. It took some inspired deductions by the astronomer William Herschel to work out that they were nowhere near planet, sized but much smaller. He called them asteroids, Latin for star-like, which was slightly unfortunate as they are not like stars at all. Sometimes now they are more accurately called planetoids. Finding asteroids became a popular activity in the 1800s, and by the end of the century, about 1,000 were known. The problem was that no one was systematically recording them. By the early 1900s, it had often become impossible to know whether an asteroid that popped into view was new or simply one that had been noted earlier and then lost track of. By this time, too, astrophysics had moved on so much that few astronomers wanted to devote their lives to anything as mundane as rocky planetoids. Only a few, notably Gerard Kuiper, the Dutch-born astronomer for whom is named the Kuiper Belt of comets, took an interest in the solar system at all, thanks to his work at the McDonald Observatory in Texas, followed later by work done by others at the Minor Planet Center in Cincinnati and the Spacewatch project in Arizona. A long list of lost asteroids was gradually whittled down until by the close of the 20th century only one known asteroid was unaccounted for, an object called 719 Albert. Last seen in October 1911, it was finally tracked down in 2000 after being missing for 89 years. So, from the point of view of asteroid research, the 20th century was essentially just a long exercise in bookkeeping. It is really only in the last few years that astronomers have begun to count and keep an eye on the rest of the asteroid community. As of July 2001, 26,000 asteroids had been named and identified, half in just the previous 2 years, with up to a billion to identify. The count obviously has barely begun. In a sense, it hardly matters. Identifying an asteroid doesn't make it safe. Even if every asteroid in the solar system had a name and known orbit, no one could say what perturbations might send any of them hurtling towards us. We can forecast rock disturbances on our own surface, put those rocks adrift in space, and what they might do is beyond guessing. Any asteroid out there that has our name on it is very likely to have no other. Think of the Earth's orbit as a kind of motorway on which we are the only vehicle, but which is crossed regularly by pedestrians who don't know enough to look before stepping off the verge. At least 90% of these pedestrians are quite unknown to us. We don't know where they live, what sort of hours they keep, how often they come our way. All we know is that at some point, at uncertain intervals, they trundle across the road down which we are cruising at over 100,000 kilometers an hour. As Stephen Ostro of the Jet Propulsion Laboratory has put it, suppose that there was a button you could push and you could light up all the Earth crossing asteroids larger than about 10 meters. There would be over 100 million of these objects in the sky. In short, you would see not a couple of thousand distant twinkling stars, but millions upon millions of nearer, randomly moving objects, all of which are capable of colliding with the Earth and all of which are moving on slightly different courses through the sky at different rates. It would be deeply unnerving. Well, be unnerved because it is there. We just can't see it. Altogether, it is thought, though it is really only a guess based on extrapolating from cratering rates on the moon, that some 2,000 asteroids big enough to imperil civilized existence regularly across our orbit. But even a small asteroid, the size of a house, say, could destroy a city. The number of these relative tittlers in Earth crossing orbits is almost certainly in the hundreds of thousands and possibly in the millions, and they are nearly impossible to track. The first one wasn't spotted until 1991, and that was after it had already gone by. Named 1991 BA, it was noticed as it sailed past us at a distance of 170,000 kilometers. In cosmic terms, the equivalent of a bullet passing through one's sleeve without touching the arm. 3 years later, another somewhat larger asteroid missed us by just 65,000 miles, the closest pass yet recorded. It, too, was not seen until it had passed and would have arrived without warning. According to Timothy Ferris, writing in the New Yorker, such near misses probably happen 2 or 3 times a week and go unnoticed. An object 100 meters across couldn't be picked up by any Earth-based telescope until it was within just a few days of us. And that is only if a telescope happened to be trained on it, which is unlikely because even now the number of people searching for such objects is modest. The arresting analogy that is always made is that the number of people in the world who are actively searching for asteroids is fewer than the staff of a typical McDonald's restaurant. It is actually somewhat higher now, but not much. While Gene Shoemaker was trying to get people galvanized about the potential dangers of the inner solar system, another development, wholly unrelated on the face of it, was quietly unfolding in Italy with the work of a young geologist from the Lamont Doherty Laboratory at Columbia University. In the early 1970s, Walter Alvarez was doing fieldwork in a comely defile known as the Bottacione Gorge near the Umbrian hill town of Gubbio, when he grew curious about a thin band of reddish clay that divided two ancient layers of limestone, one from the Cretaceous period, the other from the Tertiary. This is a point known to geology as the KT boundary, and it marks the time, 65 million years ago, when the dinosaurs and roughly half the world's other species of animals abruptly vanished from the fossil record. Alvarez wondered what it was about a thin lamina of clay, barely 6 millimeters thick, that could account for such a dramatic moment in the Earth's history. At that time, the conventional wisdom about the dinosaur extinction was the same as it had been in Charles Lyell's day a century earlier, namely, that the dinosaurs had died out over millions of years. But the thinness of the clay layer clearly suggested that in Umbria, if nowhere else, something rather more abrupt had happened. Unfortunately, in the 1970s, no tests existed for determining how long such a deposit might have taken to accumulate. In the normal course of things, Alvarez almost certainly would have had to leave the problem at that. But luckily, he had an impeccable connection to someone outside his discipline who could help. His father, Luis. Luis Alvarez was an eminent nuclear physicist. He had won the Nobel Prize for Physics the previous decade. He had always been mildly scornful of his son's attachment to rocks, but this problem intrigued him. It occurred to him that the answer might lie in dust from space. Every year, the Earth accumulates some 30,000 tons of cosmic spherules, space dust in plainer language, which would be quite a lot if you swept it into one pile, but is infinitesimal when spread across the globe. Scattered through this thin dusting are exotic elements not normally much found on Earth. Among these is the elemental iridium, which is 1,000 times more abundant in space than in the Earth's crust, because it is thought most of the iridium on Earth sank to the core when the planet was young. Luis Alvarez knew that a colleague of his at the Lawrence Berkeley Laboratory in California, Frank Asaro, had developed a technique for measuring very precisely the chemical composition of clays using a process called neutron activation analysis. This involved bombarding samples with neutrons in a small nuclear reactor and carefully counting the gamma rays that were emitted. It was extremely finicky work. Previously, Asaro had used the technique to analyze pieces of pottery, but Alvarez reasoned that if they measured the amount of one of the exotic elements in his son's soil samples and compared that with its annual rate of deposition, they would know how long it had taken the samples to form. On an October afternoon in 1977, Luis and Walter Alvarez dropped in on Asaro and asked him if he would run the necessary tests for them. It was really quite a presumptuous request. They were asking Asaro to devote months to making the most painstaking measurements of geological samples merely to confirm what seemed entirely self-evident to begin with, that the thin layer of clay had been formed as quickly as its thinness suggested. Certainly, no one expected his survey to yield any dramatic breakthroughs. Well, they were very charming, very persuasive, Asaro recalled in an interview in 2002, and it seemed an interesting challenge, so I agreed to try. Unfortunately, I had a lot of other work on, so it was 8 months before I could get to it. He consulted his notes from the period. On June 21st, 1978, at 1:45 p.m., we put a sample in the detector. It ran for 224 minutes, and we could see we were getting interesting results, so we stopped it and had a look. The results were so unexpected, in fact, that the three scientists at first thought they had to be wrong. The amount of iridium in the Alvarez sample was more than 300 times normal levels, far beyond anything they might have predicted. Over the following months, Asaro and his colleague Helen Michel worked up to 30 hours at a stretch. Once you started, you couldn't stop, Asaro explained, analyzing samples, always with the same result. Tests on other samples from Denmark, Spain, France, New Zealand, Antarctica showed that the iridium deposit was worldwide and greatly elevated everywhere, sometimes by as much as 500 times normal levels. Clearly, something big and abrupt, and probably cataclysmic, had produced this arresting spike. After much thought, the Alvarezes concluded that the most plausible explanation, plausible to them at any rate, was that the Earth had been struck by an asteroid or comet. The idea that the Earth might be subjected to devastating impacts from time to time was not quite as new as is now sometimes suggested. As far back as 1942, a Northwestern University astrophysicist named Ralph B. Baldwin had suggested such a possibility in an article in Popular Astronomy magazine. He published the article there because no academic publisher was prepared to run it, and at least two well-known scientists, the astronomer Ernst Upik and the chemist and Nobel laureate Harold Urey, had also voiced support for the notion at various times. Even among paleontologists, it was not unknown. In 1956, a professor at Oregon State University, M. W. de Lobenfels, writing in the Journal of Paleontology, had actually anticipated the Alvarez theory by suggesting that the dinosaurs may have been dealt a death blow by an impact from space. And in 1970, the president of the American Paleontological Society, Dewey J. McLaren, proposed at the group's annual conference the possibility that an extraterrestrial impact may have been the cause of an earlier event known as the Frasnian extinction, as if to underline just how unnovel the idea had become by this time. In 1979, a Hollywood studio actually produced a movie called Meteor. It's 5 miles wide, it's coming at 30,000 mph, and there's no place to hide. Starring Henry Fonda, Natalie Wood, Carl Malden, and a very large rock. So when, in the first week of 1980, at a meeting of the American Association for the Advancement of Science, the Alvarezes announced their belief that the dinosaur extinction had not taken place over millions of years as part of some slow, inexorable process, but suddenly in a single explosive event. It shouldn't have come as a shock, but it did. It was received everywhere, but particularly in the paleontological world, as an outrageous heresy. Well, you have to remember, Asaro recalls, that we were amateurs in this field. Walter was a geologist specializing in paleomagnetism, Lewis was a physicist, and I was a nuclear chemist. And now, here we were telling paleontologists that we had solved the problem that had eluded them for over a century. It's not terribly surprising that they didn't embrace it immediately. As Luis Alvarez joked, we were caught practicing geology without a license. But there was also something much deeper and more fundamentally abhorrent in the impact theory. The belief that terrestrial processes were gradual had been elemental in natural history since the time of Lyell. By the 1980s, catastrophism had been out of fashion for so long that it had become literally unthinkable. For most geologists, the idea of a devastating impact was, as Eugene Shoemaker noted, against their scientific religion. Nor did it help that Luis Alvarez was openly contemptuous of paleontologists and their contributions to scientific knowledge. They're really not very good scientists. They're more like stamp collectors, he wrote in the New York Times in an article that stings yet. Opponents of the Alvarez theory produced any number of alternative explanations for the iridium deposits. For instance, that they were generated by prolonged volcanic eruptions in India called the Deccan Traps. Trap comes from a Swedish word for a type of lava. Deccan is the name of the area today, and above all insisted that there was no proof that the dinosaurs disappeared abruptly from the fossil record at the iridium boundary. One of the most vigorous opponents was Charles Officer of Dartmouth College. He insisted that the iridium had been deposited by volcanic action, even while conceding in a newspaper interview that he had no actual evidence of it. As late as 1988, more than half of all American paleontologists contacted in a survey continued to believe that the extinction of the dinosaurs was in no way related to an asteroid or cometary impact. The one thing that would most obviously support the Alvarez's theory was the one thing they didn't have, an impact site. Enter Eugene Shoemaker. Shoemaker had an Iowa connection. His daughter-in-law taught at the University of Iowa, and he was familiar with the Manson crater from his own studies. Thanks to him, all eyes now turn to Iowa. Geology is a profession that varies from place to place. In Iowa, a state that is flat and stratigraphically uneventful, it tends to be comparatively serene. There are no alpine peaks or grinding glaciers, no great deposits of oil or precious metals, not a hint of a pyroclastic flow. If you are a geologist employed by the state of Iowa, a big part of the work you do is to evaluate manure management plans, which all the state's animal confinement operators, pig farmers, to the rest of us, are required to file periodically. There are 15 million pigs in Iowa. So a lot of manure to manage. I'm not mocking this at all. It's vital and enlightened work. It keeps Iowa's water clean. But with the best will in the world, it's not exactly dodging lava bombs on Mount Pinatubo or scrabbling over crevasses on the Greenland ice sheet in search of ancient life-bearing quartzes. So we may well imagine the flutter of excitement that swept through the Iowa Department of Natural Resources when in the mid-1980s the world's geological attention focused on Manson and its crater. Trowbridge Hall in Iowa City is a turn-of-the-century pile of red brick that houses the University of Iowa's Earth Sciences Department and, way up in a kind of a garret, the geologists of the Iowa Department of Natural Resources. No one now can remember quite when. Still, that's why the state geologists were placed in an academic facility, but you get the impression that the space was conceded grudgingly, for the offices are cramped and low-ceilinged and not very accessible. When being shown the way, you half expect to be taken out onto a roof ledge and helped in through a window. Ray Anderson and Brian Witzke spend their working lives up here amid disordered heaps of papers, journals, furled charts, and hefty specimen stones. Geologists are never at a loss for paperweights. It's the kind of space where if you want to find anything, an extra chair, a coffee cup, a ringing telephone, you have to move stacks of documents around. Suddenly, we were at the center of things, Anderson told me, gleaming at the memory of it, when I met him and Witschke in their offices on a dismal, rainy morning in June. It was a wonderful time. I asked them about Gene Shoemaker, a man who seems to have been universally revered. He was just a great guy, Witschke replied without hesitation. If it hadn't been for him, the whole thing would never have gotten off the ground. Even with his support, it took 2 years to get it up and running. Drilling's an expensive business, about $35 a foot back then, more now, and we needed to go down 3,000 feet. Sometimes more than that, Anderson added. Sometimes more than that, which added. And at several occasions, so you're talking a lot of money, certainly more than our budget would allow. So collaboration was formed between the Iowa Geological Survey and the U.S. Geological Survey. At least, we thought it was a collaboration, said Anderson, producing a small, faint smile. It was a real learning curve for us, which went on. There was actually quite a lot of bad science going on throughout the period, people rushing in with results that didn't always stand up to scrutiny. One of those moments came at the annual meeting of the American Geophysical Union in 1985, when Glenn Izzet and C. L. Pillmore of the U.S. Geological Survey announced that the Manson crater was of the right age to have been involved with the dinosaurs' extinction. The declaration attracted a good deal of press attention, but was unfortunately premature. A more careful examination of the data revealed that Manson was not only too small, but also 9 million years too early. The first Anderson or Witchkill learned of this setback to their career was when they arrived at a conference in South Dakota and found people coming up to them with sympathetic looks and saying, "We hear you lost your crater." It was news to them that Izet and the other USGS scientists had just announced revised figures revealing that Manson couldn't, after all, have been the extinction crater. It was pretty stunning, recalls Anderson. I mean, we had this thing that was really important and then suddenly we didn't have it anymore. But even worse was the realization that the people we thought we'd been collaborating with hadn't bothered to share with us their new findings. Why not? He shrugged. Who knows? Anyway, it was a pretty good insight into how unattractive science can get when you're playing at a certain level. The search moved elsewhere. By chance, in 1990, one of the searchers, Alan Hildebrand of the University of Arizona, met a reporter from the Houston Chronicle who happened to know about a large, unexplained ring formation 193 3 kilometers wide and 48 kilometers deep under Mexico's Yucatan Peninsula at Chicxulub, near the city of Progreso, about 950 kilometers due south of New Orleans. The formation had been found by Pemex, the Mexican oil company, in 1952, the year, coincidentally, that Gene Shoemaker first visited Meteor Crater in Arizona. But the company's geologists had concluded that it was volcanic, in line with the thinking of the day. Hildebrand traveled to the site and decided fairly swiftly that they had their crater. By early 1991, it had been established to nearly everyone's satisfaction that Chicxulub was the impact site. Still, many people didn't quite grasp what an impact could do. As Stephen Jay Gould recalled in one of his essays, I remember harboring some strong initial doubts about the efficacy of such an event. Why should an object only 6 miles across wreak such havoc upon a planet with a diameter of 8,000 miles? Conveniently, a natural test of the theory arose soon after when the Shoemakers and Levy discovered comet Shoemaker-Levy 9, which they soon realized was headed for Jupiter. For the first time, humans would be able to witness a cosmic collision, and witness it very well, thanks to the new Hubble Space Telescope. Most astronomers, according to Curtis Peebles, expected little, particularly as the comet was not a coherent sphere but a string of 21 fragments. My sense, wrote one, is that Jupiter will swallow these comets up without so much as a burp. 1 week before the impact, Nature ran an article, "The Big Fizzle is Coming," predicting that the impact would constitute nothing more than a meteor shower. The impacts began on 16th of July 1994, went on for a week, and were bigger by far than anyone, with the possible exception of Gene Shoemaker, expected. One fragment, known as Nucleus G, struck with a force of about 6 million megatons, 75 times all the nuclear weaponry in existence. Nucleus G was only about the size of a small mountain, but it created wounds in the Jovian surface the size of Earth. It was the final blow for critics of the Alvarez theory. Luis Alvarez never knew of the discovery of the Chicxulub crater or of the Shoemaker-Levy comet, as he died in 1988. Shoemaker also died early. On the third anniversary of the Jupiter collision, he and his wife were in the Australian outback, where they went every year to search for impact sites. On a dirt track in the Tanami Desert, normally one of the emptiest places on Earth, they came over a slight rise just another vehicle was approaching. Shoemaker was killed instantly, his wife injured. Some of his ashes were sent to the moon aboard the Lunar Prospector spacecraft. The rest were scattered around Meteor Crater. Anderson and Wich- Anderson and Witchke no longer had the crater that killed the dinosaurs, but we still had the largest and most perfectly preserved impact crater in the mainland United States, Anderson said. A little verbal dexterity is required to keep Manson's superlative status. Other craters are larger, notably Chesapeake Bay, which was recognized as being an impact site in 1994, but they are either offshore or deformed. Chicxulub is buried under 2 to 3 kilometers of limestone and mostly offshore, which makes it difficult to study. Anderson went on, while Manson is really quite accessible. It's because it is buried that it is actually comparatively pristine. I asked them how much warning we would receive if a similar hunk of rock were coming towards us today. Oh, probably none, said Anderson breezily. It wouldn't be visible to the naked eye until it warmed up, and that wouldn't happen until it hit the atmosphere, which would be about 1 second before it hit the Earth. You're talking about something moving many tens of times faster than the fastest bullet, unless it had been seen by someone with a telescope, and that's by no means a certainty. It would take us completely by surprise. How hard an impactor hits depends on a lot of variables. angle of entry, velocity, and trajectory, whether the collision is head-on or from the side, and the mass and density of the impacting object, among much else, none of which we can know so many millions of years after the fact. But that scientists can do, and Anderson and Witchke have done, is measure the impact site and calculate the amount of energy released. From that, they can work out plausible scenarios of what it must have been like, or more chillingly, would be like if it happened now. An asteroid or comet traveling at cosmic velocities would enter the Earth's atmosphere at such speed that the air beneath it couldn't get out of the way and would be compressed, as in a bicycle pump. As anyone who has used such a pump knows, compressed air grows swiftly hot, and the temperature below it would rise to some 60,000 Kelvin, or 10 times the surface temperature of the sun. In this instant of its arrival in our atmosphere, everything in the meteor's path, people, houses, factories, cars, would crinkle and vanish like cellophane in a flame. 1 second after entering the atmosphere, the meteorite would slam into the Earth's surface, where the people of Manson had a moment before been going about their business. The meteorite itself would vaporize instantly, but the blast would blow out 1,000 cubic kilometers of rock, earth, and superheated gases. Every living thing within 250 kilometers that hadn't been killed by the heat of entry would now be killed by the blast. Radiating outwards at almost the speed of light would be the initial shock wave, sweeping everything before it. For those outside the zone of immediate devastation, the first inkling of catastrophe would be a flash of blinding light, the brightest ever seen by human eyes, followed an instant to a minute or two later by an apocalyptic sight of unimaginable grandeur, a roiling wall of darkness reaching high into the heavens, filling one entire field of view and traveling at thousands of kilometers an hour. Its approach would be eerily silent since it would be moving far beyond the speed of sound. Anyone in a tall building in Omaha or Des Moines, say, who chanced to look in the right direction would see a bewildering veil of turmoil followed by instantaneous oblivion. Within minutes, over an area stretching from Denver to Detroit and encompassing what had once been Chicago, St. Louis, Kansas City, the Twin Cities, the whole of the Midwest in short, nearly every standing thing would be flattened or on fire, and nearly every living thing would be dead. People up to 1,500 kilometers away would be knocked off their feet and sliced or clobbered by a blizzard of flying projectiles. Beyond 1,500 kilometers, the devastation from the blast would gradually diminish. But that's just the initial shock wave. No one can do more than guess what the associated damage would be. Other than that, it would be brisk and global. The impact would almost certainly set off a chain of devastating earthquakes. Volcanoes across the globe would begin to rumble and spew. Tsunamis would rise up and head devastatingly for distant shores. Within an hour, a cloud of blackness would cover the earth and burning rock and other debris would be pelting down everywhere, setting much of the planet ablaze. It has been estimated that at least 1.5 billion people would be dead by the end of the first day. The massive disturbances to the ionosphere would knock out communication system everywhere. So survivors would have no idea what was happening elsewhere or where to turn. It would hardly matter. As one commentator has put it, fleeing would mean selecting a slow death over a quick one. The death, the death toll would be very little affected by any plausible relocation effort, since Earth's ability to support life would be universally diminished. The amount of soot and floating ash from the impact and following fires would blot out the sun certainly for months, possibly for years, disrupting growing cycles. In 2001, researchers at the California Institute of Technology analyzed helium isotopes from sediments left from the later KT impact and concluded that it affected the Earth's climate for about 10,000 years. This was actually used as evidence to support the notion that the extinction of dinosaurs was swift and emphatic. And so it was in geological terms. We can only guess how well or whether humanity would cope with such an event, and in all likelihood, remember, this would come without warning, out of a clear sky. But let's suppose we did see the object coming. What would we do? Everyone assumes we would send up a nuclear warhead and blast it to smithereens. There are some problems with that idea, however. First, as John S. Lewis notes, our missiles are not designed for space work. They haven't the oomph to escape Earth's gravity, and even if they did, there are no mechanisms to guide them across tens of millions of kilometers of space. Still less could we send up a shipload of space cowboys to do the job for us, as in the movie Armageddon. We no longer possess a rocket powerful enough to send humans even as far as the moon. The last rocket that could, Saturn V, was retired years ago and has never been replaced, nor could we quickly build a new one because, amazingly, the plans for Saturn launchers were destroyed as part of a NASA spring cleaning exercise. Even if we did manage somehow to get a warhead to the asteroid and blast it to pieces, the chances are that we would simply turn it into a string of rocks that would slam into us one after the other, in the manner of Comet Shoemaker-Levy on Jupiter, but with the difference that now the rocks would be intensely radioactive. Tom Gerals, an asteroid hunter at the University of Arizona, thinks that even a year's warning would probably be insufficient to take appropriate action. The greater likelihood, however, is that we wouldn't see any object, even a comet, until it was about 6 months away, which would be much too late. Shoemaker-Levy 9 had been orbiting Jupiter in a fairly conspicuous manner since 1929, but it was over half a century before anyone noticed. Because these things are so difficult to compute and must incorporate such a significant margin of error, even if we knew an object was heading our way, we wouldn't know until nearly the end. The last couple of weeks, anyway, whether collision was certain. For most of the time of the object's approach, we would exist in a kind of cone of uncertainty. It would certainly be the most interesting few months in the history of the world, and imagine the party if it passed safely. So how often does something like the Manson impact happen? I asked Anderson and Witchko before leaving. Oh, about once every million years on average, said Witchko. And remember, added Anderson, this was a relatively minor event. Do you know how many extinctions were associated with the Manson impact? No idea, I replied. None, he said, with a strange air of satisfaction. Not one. Of course, Witchko and Anderson added hastily and more or less in unison. There would have been terrible devastation across much of the earth, as just described, and complete annihilation for hundreds of miles around ground zero. But life is hardy, and when the smoke cleared, there were enough lucky survivors from every species that none permanently perished. The good news, it appears, is that it takes an awful lot to extinguish a species. The bad news is that the good news can never be counted on. Worse still, it isn't actually necessary to look to space for petrifying danger. As we are about to see, Earth can provide plenty of danger of its own.